Okay, so what I'm going to do is I'm going to find one of the problems in this section that has acceleration. Okay. Oh, I jumped way over here. Okay. Okay. Okay, so in here, he has. Oh, the projector's not on. Sorry about that. So we'll have to give it a minute. I think I'll get a drink of water. Okay, doesn't do a great job of laying this out, so I think I'll just slip in here and do a little better job of laying this out. So, and I'll kind of cover that. Let me go backwards up one, where that came from, and start right there. I might be able to fit it all in that little area there. Okay. So each one of these terms, if you look up here, and I'm going to move this one. Well, I'll do this. I'll do it the way he's doing. Plus velocity of v relative to a. But we went through this and found out that term is nothing more than the omega AB, whatever length that is, crossed with RB to A. So this term is actually that term. So if you do start taking the derivatives here, you take the derivative of b, you get the acceleration of b. Oops. Okay. And then if you take the velocity of the point A, you get the acceleration of A. And then you start looking at this one's different because this is taking a derivative on that. So if you look at it, you bring this down, you're taking a derivative, AB, rotation across R, B to A. Oops. I gotta finish it out with respect to time. So what you do is you take a derivative of this times that. So what you do, take the time derivative of that, cross R, B to A, plus the time derivative of that, you get AB, crossed with the time derivative of R, B to A. And technically, so I don't mix, I think I'll do this. I'll say, do I not have an eraser here? But this term becomes a new term that we talked about before, which is just alpha AB, which is a vector as well. So this term just simply becomes that. You know, it becomes alpha AB cross RB to A. But this term is actually the same thing as that term, which is in fact this term, which can be written as omega AB cross omega AB cross R beta A. Now, looking at the complexity of this term, we find out something interesting. If, say, I wonder if he has a good drawing. I'll try to do the best drawing I can. So say you had something rotating about an axis here, spinning right here. So you're out here at some point. Okay, so if it's spinning that way in omega, let's just call this A, this B, just for, so omega AB looks like that. And then R looks like this term right here. So let's take this term. So here's your R. Depends on the way you want to look at it. So let's see, BA. So you got that, and you got this. So this is the vector altimeter. If you look at the cross product of this, you take your fingers and you put up in this direction, and you rotate it around, and what you're getting is, this is the velocity VA, and it's perpendicular to that. Now you take that vector, okay, so I'll redraw it. I'll take this vector and move it over here. So I'm going to take this vector and move it to this point. Here's your velocity VA, and you have this vector, which is omega AB. It turns out that if I move it back there, those vectors are 90 degree too. Remember, the resultant of a cross product is always perpendicular to each component that produced it. Now, I'll look at omega cross this. So take my hand, move it there. It's actually going, I'm drawing it in a funny way. It's going this way, which basically is the opposite direction of the R. So what he does is he says, hey, it always is the opposite direction of R, therefore this thing will always be omega squared magnitude squared, because you got two of them, and the vector R beta A, but there's a minus sign in front of it to indicate it's always in the opposite direction of the R beta A. So if you scroll down, you'll see that, and then you'll see, okay, you'll see that term. So, in fact, what is this? Well, of course, that's that one. This is this one. Okay, this one, there should be a plus sign right here. This one is, in fact, that one. And here's your minus omega squared, and this is the vector. This indicates it's going in the opposite direction. So that's like the centrifugal component. If a car is going in a circle, and you have a velocity out here, its centrifugal acceleration goes this way, the opposite direction, in towards that, in this case, point A. So that's why this term exists right there. So now you've got an equation of acceleration components. And this is kind of a weird way of looking at it, but other books, there's another book, I can't think of the authors right now, but they leave it in this form. And that's okay. He actually makes a breakdown and says, okay, this will always be that. And so the calculations, you can just do that. So let's go do a problem with this. Okay,
let's see what that example looks like. We could do that one, but let's look at another one and see what this other one looks like. That one actually is less boring. I'd like to see one that has a connection, a bar, and a slider. That doesn't have one. Oh, I think I jumped. I think I ended up not moving to the next one. If I have to give up these, and okay, that's okay one. We'll do that one. And if I do that one, do I get more room? If I do that, get a little bit more room. Okay, so let's do that one. We know it's done below there anyway, but we'll just go through the case. Okay, so he says, he gives all the stuff here. He cheats in a way. That's not fair. Okay, so the collar moves down, acceleration of that, and an instant shown the speed is that, which it gives the length CV the angular velocity of that. Now, that's kind of cheating because actually what we'll do real quick is we'll prove this and then determine the angular acceleration of the CB and AB at the instant. So first let's prove that. We'll do it with instant center. And this is kind of weird. Okay, so he tells us this and he tells us that. But we have this and this. So let's do an instant center to see if we get this and to see if we get that. Okay, so all we do is look at each length. So I'm going to look at AB. And AB tells me A sitting still. So if this thing is rotating, it's got to either rotate this way or this way. I don't care which one, just that I know its direction. Once I know its direction, I'll pass, I suppose, a perpendicular straight line, but it's a little wiggly. This one, I know it's going down because he told me, but it really doesn't matter which way it's going. It just matters that I know the direction it's going. And so I'll pass perpendicular through there. So the instant center of, okay, now I found B, I found C, so this is BC, is right there. And it just so happens that this is 0.2 and this is 0.2. So now let's look at the velocity of whatever. Let's look at the velocity of C. So the velocity of C is equal to omega times r. But this is omega. C sits upon this rod whose instant center is there. I was told the velocity is going down with 2, so I have to obey that and say it is going down at a velocity of 2. So that velocity is 2. It came from the problem statement. When I'm looking at the omega, here, let me put the subscript here. This would be omega BC or omega CB. It doesn't matter which one it is. He's listed it as CB, but it doesn't matter. Times R. Now this is the R from the instant center to the point C. So that actually, let's see, it really doesn't matter, it's the magnitude. So I'll just say instant center to C. How about that? That's a weird subscript. But now I don't know omega BC. I know he told it to us, but I don't want to buy into that yet. The distance between here and here is 0.2. You divide this out, omega BC is equal to 10. And we're okay with that. If that's the case, it's kind of weird that the instant center of this rod sits at the instant center of this rod. That's only because this is the same length as that, and this thing is at 45 degrees and several geometries here. So now I can say the velocity of point B now that I know, see, this is what's weird is he puts it out here, and that's okay, but in a mental sort of state, this is weird. You erase this link and erase this, and you say this is omega BC rotates this way. So that means this velocity is true and that one's false. And it's moving to the right. And what is that velocity? Well, it's 2 meters here, I'm sorry, 0.2, times the omega of that thing, which is 10, which gives me that's being 2. And now, only at this point can I say, okay, I'm no longer going to concern myself with link BC. I'm only going to say to myself, I'm looking at AB. And so the velocity of point B as it exists on omega AB, and then the R from here to here, well, it's still 0.2. This, I don't know, but B is 2. And so omega AB equals to 10 as well. So we've picked that, and we've proven that it's the case. So now that we buy into this, let's go ahead and do the rest of this right here, which is find the at the speed center, which gives links BC. Okay, determine at the instant show, so it gives links determine the angular acceleration of CB and AB at this instant, as well as finding the acceleration at this point. So now we have everything. So now let's go in and do this. We got to link C and B. So we got to link C to B. We have that one. We have a link B to C, sorry. So we have 2 links. This one and that one. And since I don't know which one would be the best to do first, but I think I'm going to do this one first. If I'm doing it this way, I'm going to go ahead and pick up my coordinate systems and write this as a reference, X and Y, and a positive omega and a positive alpha. And we'll just do this one first, because then it'll give us a reference to that point, and then we'll write between these two. So I don't know. Acceleration of B is equal to acceleration of A, that's the A, which is nothing, plus the acceleration of B relative to A. And this term, okay, so this is 0, and so now I can say the acceleration of B is equal to, and what is it equal to? It's alpha AB, the vector, crossed R B to A, minus the omega AB, the magnitude. It's a vector, so take its magnitude, square it, and B to A. So this will be the centrifugal part. This will be the tangential, which is usually or along ST, whatever. So we do not know. What do we not know? That. We don't know that. But now we have to come up with this as a vector. And luckily, he set our geometry nice. We have our coordinate system. So position of B relative to A is a vector that starts at A, ends at B. So it's minus in the y direction, and it goes down 0.2 distance, and it's just that simple. In the meantime, well, I would just stick here. I was about to say I was going to find the one from here to here, but I'll wait till I get to that. So right now I'm here with this. Now I turn around, I have to use that over here in several places. So the other thing, when I'm going in here finding the unknowns, I always assume positive alpha, and for that matter, positive omega when I'm working on velocities. But I'm working on accelerations here, so I'm going to assume it to be positive. So if I look at this thing, this is a cross product. This is actually 1, 2, but it's already been broken apart for us. So I do I, J, K. I'm going to assume it to be positive. Assuming it to be positive means it's a positive number there. Then all I have to do is get that vector, which is this, and put it in there. So I've got that component. Now I'll subtract off, well, this was told to us to be that magnitude, so that's actually 10 squared times the vector that's right down here, which is 0.2 minus 0.2j. Now let's see. If I look at this, I go in the j component here and do a determinant of these two and these together, I get nothing. Of course, if I do the determinant with the k, I get this times that, nothing. So the only one I get is associated with the I, and that is the I times 0 at alpha AB minus 0.2 and 0, and then I get, I don't know, I get plus, because this and this go together. I get 100 times 0.2, which gives me back 20j. This part I hadn't figured out yet, but okay, let me go back. And I'm just going to leave this as the acceleration of b for the moment. And just going to leave it in that term. And now I'm going to do this. This times this gives you 0. A minus that times that gives you minus 0.2 alpha AB and an I right here. So that's all you get there. And so what I'm going to do is I'm going to take this equation and stick it like right here maybe. So I'm going to say, put it at an angle. Acceleration of B is equal to I minus 0.2 alpha AB times I, and then plus 20j, unless I calculated that wrong. I think 100 times 0.2 gives me back 20, I think. So sit there and look at that and think to myself, okay, what did I accomplish? Well, I didn't accomplish much except the fact that I've done the link and B exists on both of these. So now I can write the equation for this link and put the B's together. You know, the acceleration of B is the same whether it's on this link or on that link. Means that B, acceleration B, I can eliminate here. So maybe I'll use this area to start that. It'll be a little bit more complicated, so I wonder if I should just go back over to there and erase that. But here, let me, while we're doing this, let me give you a second and I will go. I want to just make sure that go here. Oh yeah, there I am. So we're doing fine. So I'll go ahead and erase this and do this, okay? So what I'll do, actually, you know what I'll do? I'll do it a step at a time. Acceleration of B on this link is equal to acceleration of C plus the acceleration of C relative to B. Okay, this time, acceleration of C is actually known. So the acceleration of C in a vector form is actually minus, it's going down that way, that coordinate is just that. So believe it or not, I can sort of back up and say acceleration of B is equal to minus J, you just don't need to put the 1, plus, now I'm on length CB. So what I'll do, okay, BC, CB, the same mode of indices go there as well as there. Now, this is BC. Oh, I already had the, okay, hang on. And then R, C to B. Now, it turns out, okay, so let's say minus J plus acceleration of B equals it. Now I need to find this vector, the vector that starts out at hang on a second. Got that flipped. Okay, this has to be BC. Sorry about that. Now, I was going too fast there. So, so now I need to go find the vector. I looked over and realized I had the wrong vector here. So I noticed I had the wrong subscript. So I got to find a vector that starts at C. Okay, let me erase a little bit here. Starts at C, goes down to B. So that vector is actually pretty easy. So R, that's the vector that goes from C to B, is going to go this way, 0.2, and it's going to go that way, 0.2 as well. So you get this vector. So we'll be using this over here. So what do I do? I first go in that, put that in there, this one in here. Then I can just copy that down and put it right there. 0.2i minus 0.2j. This, I think I could do the math here. So let's see, minus. This one, I probably need more room. And I'll just figure out how to fit it in here, and then the results I'll put right over here. So if I'm going to do that, I'm going to move this out of the way. I'm having limited board space here, so that. Okay, so now I know that's 100, and that's going to break it down to 20. I, and those two will go together and be 20j. Now, this time, the I component is going to get some, and the j component is going to get some. So here, plus. Now I'm just going to pull out the I component. Clear, and 0 alpha. And it's 0.2 of nothing. And minus j. It's going to be something funny that ends up out here. The j, 0, alpha, 0.20. What's funny is the minus sits here, the minus sits out here, and a plus in there, so these two become the same. I should also be meticulous and put the BC here. And so you end up with this, and of course the minus j sits there. And plus, okay, that times that, minus that times that. Well, there's already a minus, So you get a 0.2 alpha BC I. That and that minus that comes that, but then you have a plus here, but you get a minus there, so you get a plus 0.2 alpha BC. And so let me copy this over there, if you don't mind, and I'll say this. Acceleration of B equals to minus J plus 0.2 alpha BC, and that is I. Shoot, I'm going to run out of space. But I guess I can run off into the dark area. Let me see. I don't even know. Sometimes things just don't work. Okay, that camera is not working there. So I guess, let's see. Let me look here. Oh yeah, I've got the dark space over to the right I can use. Okay, so I can use the dark space over to the right. So I get this, and then I get a plus 0.2 alpha BC J from that term minus 20I plus 20J. So this all came from that link, but I also have this information from this link. So what I can do, this sounds weird, but I'll put this to the left. Minus 0.2 alpha AB I plus 20J. So this is from link AB, oops, and this is from link BC. B is common amongst them both, so that's why I expressed that one as acceleration B, and this one is acceleration B. Get all done, I can take this and set it equal to that. If I do that, now I can turn around and take the I component. I can take this one, I can take that one, and I can take that one. Put them all together. So I can say minus 0.2 alpha AB has to be equal to 0.2 alpha BC from that one, minus 20. And then I'll take the J component. That would be this one, and this one, and that one, and that one. Here we get the extra one, but it's okay. Okay, so on the left hand, I get a 20 equal to minus 1, so I can just move that over, but not yet. And then the one here plus 0.2 alpha BC, and then plus 20. Okay, did I do that right? Okay, notice, okay, wait. Let's just make sure. We notice one thing that's kind of, and this, I think, is designed into this problem, and that is that the fact that it's straight down the AB link, I don't get anything else in there, so I've got this, I've got the 20. So what I'm getting at, the fact that that link is straight down means that if I tilted it off, I'd have another component associated with the alpha AB. You notice the alpha AB is because of this term and the fact that that vector was straight down meant the tangential acceleration only moved in the x direction. There wasn't a y component. So it simplified this part. So I think I can get rid of that and that. I can move that over, and I can get alpha BC equal to 5. Now, for me to find out where I am in this, I'm going to go rolling down. Okay. So what was that, AB? So if I roll down, okay, he's doing this. Here's the acceleration. Okay, there's the 0.2. Uh-oh. made a mistake. Wait a minute. Where did it go? Okay. Plus 20. I think I may have made a mistake there. Okay. The end result. I'll go back and find my mistake. The end result of that mistake will be, well, yeah, the end result of that mistake is my alpha will go the other direction. But let me track down my mistake before I claim it. And let me go back and fix that. Okay. One more down? No, one more up. I can't really tell. Oh, no, another one up. Okay, let me see if I can fix my mistake on that first one. On that first one, okay, so acceleration of B equals acceleration of A, which doesn't exist, plus omega AB cross R. You know what? I may have done this. It's got to be B relative to A. So I start at A, draw down. I have a vector this way. This vector becomes minus 0.2j. So now, let me go in here. Before I claim there's a mistake, here's the thing. I, J, K, 0, 0, omega AB. He may have done something opposite to what I would do. And in that case, here's what I'm going to look at. So I'll say alpha BC is equal to 5 in this direction. So let's take a look and see if his answer showed up that way. Because, let's see. So we both got the right answer. We both did it correct. But what he did is he did something interesting. Alpha BC CB, which BC and CB are the same. We got the same answer, but his equation looked different. So why did his equation look different? Because, okay, where did he talk about this? Okay, I'm trying to find out where he talked about this. And this is something you can find yourself tracking down. And that's why I always go to this sign convention here, and I always assume a positive because I don't want to get confused. Now, it looks like he has this as a positive. Unless he's assuming that this is this direction. I want to know, how is he assuming that? And the way we'll find that out is see when he puts his equation together. And this can make it complicated when you start learning this kind of stuff. Okay, so if we look at his, I don't know that I need this information here. So let's take a look at his equation. And so he immediately goes down and says, this is K, and this is minus 0.2. That's what we got here. Now, did I make a mistake in the matrix itself? I, J, K, and then alpha AB, and then minus 0.2. Okay, so out of that, it's only going to become an I. So you get a 0, an alpha AB, a minus 0.2, and a 0, and an I. That times that, minus that times that, that does become a plus. So he is correct there. And so I made a mistake in my cross products where I extracted that out, and somehow I made that mistake that is right there. But if we go further, what we find out is that mistake is only propagated to right here. and that would be, put a plus right there. So that mistake doesn't see itself into this equation. So in fact, we did find alpha BC. It would only come out in this. And so I did make that mistake. That should be a plus. I let it slide. That's just the way things go sometimes. So it's okay. He assumed it to be positive. It came out. We got to 0.2. Wait, 0.2. This should be, I'm going to just draw a circle around it and do this. And I'll draw a circle around that and do that. So that's my mistake that exists here and exists here. Didn't affect this one at all. Let's go down to the next part, which I think he's doing down here. And hope he's actually assuming. He assumes alpha to rotate that way, which is the same way here. So it looks like he's doing the same thing I'm doing. He's assuming it to be positive. So Lipschitz goes down a little bit more. And there's his equation, which we digested our problem. And we got AB, which is the same thing we got, AC, which is -1. He's again doing the same thing, assuming it to be positive. This time he crossed the thing. You got that. Now, had I been doing the checking, I would have, no, I don't think I would have got that. There would have been no way to check that out. But anyway, so 0.2, 0.2, 0.2, 0.2, 0.2, 0.2, and then the -20 and the +20, the -20 and the +20, and then, of course, I already talked about that, and that came from the last one. So the problem I made, the mistake I made right there without the sign, only propagated itself to here, and so then what he's got this equation, which is the same as what I've got. He'd have got 5 out of it and stuck the 5 back in here. So 0.2 times 5 -20 equals to 0.2 alpha AB, where I would have had a minus because I stuck the minus there. And, whatever that number is, you can divide that out. And let's see what he got. Okay, so he ended up with, behind this is a -95 radius per second squared. So outside of the bump in the road I placed right in front of us early on, the first thing I recognized is he is assuming all the alphas to be positive. In other words, he is seeming to follow the sign convention like that. What he's doing along the way, though, is he's doing this to this, and that's okay if you can get used to doing this. Myself, I would rather put it in a determinant form and do it that way. So, okay, so I guess we're running over, but I started late, and I'm trying to see, I don't know if anybody's even waiting for the next class. Maybe he is, I don't know. But, sorry for the minus sign.
That's okay.
Yeah.
We gotta figure it out.
Yeah. It's just the way life is. Minus sign, plus sign, going the backwards way, Hey, it looks like these things have a little, that's interesting. Uh-oh. They have, I guess the equations are offset. So I guess if you increase it, it's still there. Oh, and it looks, oh no, wait a minute. It looks like that's, okay, this is this problem. It looks like that's the other problem.
In this video, you'll be able to test your understanding.
Huh.
The next thing to do
Oh,
is the
maybe
cross
that's all
product.
of them.
And finally, we need our formula.
That may be all the
The
problems
J
worked
components
out.
Between points C.
Yeah, it looks like it.
Express that.
He did it in 10 minutes. Oh well.
He likes to skip steps.
Yeah. Oh, does he?
Well, I mean, like, suddenly flash his work
Oh.
and not talk through it.
Oh, really? Okay.
So that's how he goes so fast.
Well, hey, then I guess I am being paid for something.
Yes, sir. Have a good day.
You too.